Hello, welcome to the webinar From Oxide to Sulphide, Creating Value with Additional Life of Mine Gold Production. My name is Scott Martin, and I'm the Sales Director of the Americas for Glencore Technology. Your presenter today is Rebecca McKechnie, Solutions Metallurgist at Glencore Technology. Before we begin, just some quick housekeeping. You'll find you are muted. This is to keep things quiet for the webinar. Ignore the raise hand icon. Instead, use the Q&A icon for any questions. And on that, feel free to ask your questions anytime along the way. At the end, while the webinar is closed, we'll still be on air, quietly taking your questions on the chat. Over to you, Beck.
Thank you all for joining us today as we talk through maximizing gold recoveries to extend the life of mine of an operation and in turn increase project value with a focus on some of the technologies that Glencore Technology offer that can assist in this. So as an overview of what we'll be covering today, we're going to be delving into the progressive decline in recoveries that might occur as we move from the higher free milling oxide component of a deposit through to the transition zone and then down deeper into the primary sulphide mineralization. So today what we're going to be looking at is how we can shift recoveries as they decline and move back into that area of higher recovery. So at a high level, all deposits are made up of different layers of varying mineralogy, and these layers exhibit quite different behaviors in terms of their response to processing options that are available to treat them. So due to the exposure to elements, the topmost layer that we see here towards the surface, they're dominated by weathered oxidized materials. So the gold contained within this layer is usually quite amenable to direct cyanidation. And as a result, processing this part of the ore body is actually relatively easy. It comprises a simple circuit, and we'd often refer to this as free milling. But as we move down lower to the ore body, we then start to encounter this transitional area where we've got both oxidized material and sulphide material coexisting together. So the gold associated with this oxidized material remains amenable to direct cyanidation, but now we've got a percentage of that gold that exists locked within the sulphide materials that are present, and this isn't as readily recoverable via cyanide leaching. And then finally, as we move down into the lowest parts or the depth of the deposit, this is dominated by the unweathered sulphide material where the majority of gold is actually locked within that sulphide matrix. So recovery of the gold via a conventional cyanide leaching without any form of additional pretreatment is typically poor from this particular region. So despite the additional complexity in being able to recover gold from sulphide minerals, the treatment of sulphide deposits is still an important consideration because these deposits do actually constitute a notable percentage of gold that's contained in reserves and in measured and indicated resources. So particularly for countries like North America, you can see where refractory deposits actually account for more than a third of the contained gold in the region. So how does an operation go about recovering gold and addressing the challenges associated with declining gold recoveries as they mine different parts of their deposit, from that oxide zone down through to the sulphides? So initially, as we're mining the oxide ores, that gold is quite readily amenable to cyanidation. So we get high recoveries, typically in that 80 to 90%, via what is quite a relatively simple circuit, as you can see on the screen here. So after the ore is mined, it moves through the required stages of crushing, grinding, before then advancing to the cyanide leach plant and final doré being made on site. However, as the operation progresses into that transition zone, the refractory gold that's locked within those sulphide materials, as I said, it's not readily recovered via the existing conventional cyanide leaching circuit. So overall, the recoveries for the operation begin to shift and will be lower as gold is progressively lost to tailings. So one approach to this, sulphide minerals can actually be readily separated from oxides via froth flotation. So the addition of a bulk flotation circuit after comminution would allow for the generation of a sulphide concentrate that may in fact be sold. And then the cyanide amenable gold in the tails of the flotation can continue to progress down the existing cyanide leach circuit. So from Glencore Technology's perspective, one of the technologies we offer is an established and quite innovative solution in froth flotation, and that's the Jamieson cell. So the Jamieson cell was developed nearly 40 years ago, and there's actually over 500 installations of this cell in the world today, all around the world. And about 40 or over 40 of these are installed specifically in gold and PGM operations. So whilst the Jamieson cell has its origins in cleaning duties, it's been progressively applied more and more in roughing capacities as well. And we even have Jamieson concentrators, so concentrators that solely exist of Jamieson cells now around the world. So the Jamieson cell itself, it's a high intensity flotation cell in which the pulp and the air are brought together in a vertical tube called the downcomer. And we'll look at the downcomer more closely in just a moment. But the design of the downcomer, in essence, does eliminate the need for agitators and for blowers. And as a result of this, the Jamieson cell itself has no moving parts. It incorporates a froth washing system, which actually removes entrained gangue from the froth, allowing the Jamieson cell to achieve higher concentrate grades relative to its counterparts. And overall, that has really contributed to its success in roughing and scalping duties because an initial product can actually be generated that has a high enough grade to be sent direct to final concentrate. And obviously, this minimizes losses that are associated with cleaning, can reduce the size of downstream regrind circuits and other cleaning cells as well. So this is a B series Jamieson cell, that's the round one. As you can see here, basically slurry is pumped up into the center of the cell, into that centralized slurry distributor you see here. And from there, the slurry then feeds into each of those arms. Each of those is a downcomer. And this is where the actual mixing occurs. So basically, the pulp is introduced into that downcomer through a converging lens you can see on the right of the screen here. And this produces a very high velocity jet. And that jet draws in air from the atmosphere and entrains it into the head space. So at the same time, a vacuum is created and that pulls slurry up into the downcomer as well. So the jet plunges into that slurry. And due to the very high shear associated with that velocity, basically very fine bubbles are generated and really intense mixing. So the air and the slurry are incorporated together and a very intense mixing process occurs. So the intense mixing forces or facilitates bubble particle interactions within that downcomer, and this is done in a matter of seconds. So the residence time in a Jamieson cell is in fact seconds, and what this means is that one Jamieson cell is actually able to replace several tank cells. So inside that downcomer, we've got a dense foam that is produced before the pulp then discharges into a separation tank. The mineral-laden bubbles will rise to the top and form a froth layer, and subsequently that is then collected in the concentrate launders. Now, to actually maintain that jet velocity and the optimal function of the Jamieson cell, pressure to the cell itself needs to be maintained at about 150 kPa. And so to ensure this, while also accommodating for those variations in plant throughputs that we would typically see, the Jamieson cells are equipped with a recycle mechanism. So a percentage of the float tails will in fact be recycled back to the feed box to maintain that constant flow to the downcomers. So this is controlled via a pressure sensor and a valve, and the valve basically just opens and closes as required to actually control how much or how little tails are returned from the fresh feed or to the fresh feed. And this is based on how that volume of fresh feed itself is increasing or decreasing. So as I mentioned, that design of the Jamieson cell results in a residence time of seconds. And so residence time isn't a consideration when we are sizing or designing these cells or these circuits. And a single Jamieson cell is capable of replacing several tank cells. So from a whole of circuit perspective, what you can see on this slide here, it's the parts of a conventional concentrator which would be replaced by a Jamison cell. So each Jamison cell is designed to either target grade or to target recovery, meaning that each cell in the circuit is given a single task. So the units that are focused on grade will be operated with deep froth and high wash water, while the units that are focused on recovery will typically be operated with higher air flow and shallow froth depths. And from here, the liberated material is obviously removed from the circuit as early as possible. You can see the example of the rougher scalper there, in which the concentrate it goes straight to final con, and that's to prevent any overgrinding or potential losses downstream in the cleaner circuit. So in being able to actually replace multiple tank cells with a single Jamison cell, obviously there are some significant opportunities for both CapEx and OpEx savings with these circuits. So fewer tanks obviously means a smaller footprint, and subsequently we've got lower requirements for concrete or for structural steel, and the installation costs that are associated with these can therefore be lower as well. We've had savings like these realised by operations like Hudbay's New Britannia concentrator. So an intended 11 tank cells were replaced by just 4 for that particular operation, and a more recent installation in the CIS in which a potential 63 tank cells were in fact replaced with 19 Jamison cells. So footprint savings of up to 50% can be achievable. And as the Jamison cells have no moving parts inside them, as I mentioned, there are also significant savings associated with things like power costs, and fewer costs associated with spares and maintenance as well. So the actual sizing and design of Jamison cells or a Jamison concentrator can actually be quite easily achieved with simple kinetic flotation tests coupled with what we call the 3-stage dilution test. So that's the test that's designed to generate a grade recovery curve for a Jamison cell or Jamison cell circuit, and to actually understand the effect of the wash water on the grade of the products. So this test, it's performed in a standard Denver cell, can be performed by any laboratory that has flotation capabilities. The actual procedure is readily available. And overall, that 3-stage dilution test, it scales 1-to-1. So there are operations like Pogo in Alaska that have installed Jamison cells that are based on just this type of bench scale work alone. But where we have more, either more difficult feeds or more complex circuits, there are Jamison cell test rigs and pilot rigs that can be available to be used to investigate the potential for the Jamison cell. So in the middle picture here is the L150. This is a laboratory scale Jamison cell, and there's a number of these in different laboratories around the world. And we also have the L and Z500 pilot rigs, which you can see on the right-hand side here. So these are rigs that are typically sent to operating sites. We provide the training and support for the use of these rigs, but ultimately it's the site themselves that have the opportunity to really run this and to test the performance of the Jamison cell within their existing circuit. So now I'm going to actually pass over to Mahe, who she's going to talk to you about the L500 work that she recently performed at Agnico Eagle's Goldex site.
Thanks, Beck. Hello, everyone. My name is Mahe Ochoa, and today it's my pleasure to present an overview of the Jamison cell pilot test we conducted at the Goldex mine. So first of all, on behalf of all my colleagues and myself, thanks Glencore Technology for having us today. So just a quick introduction to give you an overview of the Goldex complex. So it is located in Val d'Or, Canada, and it's part of Agnico Eagle's operation. The complex includes 2 mines. So the first one is the historic Goldex mine, which is an underground gold operation, and the Akasaba West mine, that is an open pit copper and gold operation that began production in 2024. So the current flow sheet is a conventional SAB comminution circuit with classification via hydrocyclones, followed by gravity separation that produces doré by recovering around 70% of the feed gold. Next, the flotation circuit consists of 6 mechanical cells and a column, producing a copper gold concentrate, which is sent to another plant for further processing. And finally, of course, we also have a tailings management circuit. To give you some numbers of our plant, so the plant processes around 8,750 tons per day, and the final concentrate has a grade of around 15 gram per ton gold and 3% copper. So I know it seems very low for a copper concentrate, but it matches with very low feed grades that we have. Okay, so now why we wanted to try the GEMS and cell technology. So after conducted process mineralogy and analyzed plant data, we identified area where we could make improvements, and the flotation circuit was one of them. So this is why we decided to test the GEMS and cell technology, and we had three main reasons. The first one was to evaluate grade recovery performance of the GEMS and cell technology to benchmark against existing circuit equipment, of course, to optimize our production. The second one was to improve fine particles recovery of copper and gold-bearing minerals, because we know that the hydrodynamics of the cell can help us for the specific application. And the last one was, of course, assessing feasibility of producing a higher quality concentrate that will help the next processing. Some number for the pilot test. So we decided to focus mainly on two streams, so the rougher feed and the cleaning feed. As you may see on the screen, the circuit is very simple with the 6 mechanical cells and the column, and we try it just here, just after the conditioning tank for the rougher application, and just before the column flotation for the cleaning application. So we tested the first streams in order to compare the GEMS and cell performance single pass with our existing entire circuit. And the second stream was chosen because we believe that the column may not be the optimal equipment for cleaning duties right now. Also, the test lasted 2.5 weeks around. And in order to obtain a grade recovery curve, we performed a design of experiment using froth depth, air flow rate, and water flow rate as parameters. And yeah, some results and outlooks. So I will just give you some highlights. But for the rougher application, the result of the pilot test have been promising, and we are really happy with that. The GEMS and cell significantly improved the copper concentrate grade, achieving around like 3 to 4 times the current concentrate grade. So from 3 to at least 10. So it was really, really good for this part, but it's still maintaining comparable recovery rates to the entire flotation circuit. And additionally, we have both gold, copper, and recovery, gold recovery and grade that shows enhancement compared to the existing rougher circuit. And about the cleaning stage, we faced some challenges due to feed variability from the plant, which made it difficult to fully assess the benefits of the GEMS and cell under these conditions. So we think that we will need a new setup to address these issues and determine the potential of the GEMS and cell for this application. So yeah, I think this is it for the overview of the pilot we've done at Agnico Eagle Gold X Mine. And just lastly, I just wanted to add that if you are coming to World Gold SME Denver, we are giving a presentation on these topics on Wednesday. And also I believe that the conference paper is available on Glencore Technology website if you want to have more details, and of course you can contact us as well. So yeah, back to you, Beck.
Thanks, Mahe. The results at Goldex really showed the flexibility and opportunities for the Jamison cell within the different parts of their circuit. So that included roughing and cleaning, and how we might be able to actually increase recoveries for existing plants via what is still a relatively simple circuit. But is the opportunity to produce and sell concentrate suited to every operation? Unfortunately not. As we know, there's a number of factors that will affect whether a site can actually produce a concentrate, including whether a saleable grade can even be achieved in the first place, potential impurities that might restrict the sale of a concentrate, arsenic being one that we're seeing quite frequently now, the specific laws within a jurisdiction that may prevent the actual sale of an intermediate product like concentrate, the cost of freighting, we've got scope 3 emission considerations, and in some cases it may actually just be that more value can be added to a project or an operation by producing final metal on site. So what does this mean for processing routes if a saleable concentrate isn't an option? So for many, the addition to the sulphide flotation circuit would be a fine grind ahead of the leach train, just to better liberate and expose the gold particles and make them more amenable to direct cyanidation. And so for Glencore Technology, this means an isomill. So the isomill is our horizontal stirred mill that provides efficiency in fine and ultra-fine grinding, quite well established. So we've got more than 150 installations around the world, and 60 of those specifically are actually in gold and PGM operations. So how does the isomill work? We start with feed being pumped into the mill on the left-hand side. You can see it enters the mill chamber, which consists of that horizontal shaft with the discs actually mounted on it, and this rotates at high speed, so about a tip speed of 20 meters per second. And the discs provide this very high intensity mixing environment with ceramic grinding media and slurry. So the coarse particles, as they move through, they tend to centrifuge out to the outside of the mill, while the finer particles are displaced towards the actual shaft and move quickly towards the discharge end of the mill. At the discharge end, what we have is the internal classifier. So basically it's a product separator, and this is unique to the isomill. So the product separator classifies fine particles from the coarse particles, and thus prevents any overgrinding by sending the coarse particles back to the beginning of the mill, giving them a second chance to pass through. And in this way, that internal classification system basically ensures a very nice tight size distribution when we're using the isomill. So that tight size distribution contributes to more predictability and better performance within circuits. And it's very much achieved in the isomill by moving that coarser top size, or that P98, closer to the target grind, or the P80. And so this reduction in size of those coarsest particles, it has significant benefits for downstream leaching processes. There's a much better chance of actually liberating that gold and making it more amenable to cyanidation. The mill also uses low SG ceramic media, so that minimizes any unintended or undesirable surface chemistry effects that may be experienced if using steel media. And additionally, lower media obviously attracts lower costs. Now, the horizontal configuration provides significantly easier conditions for mill maintenance. So obviously the shell of the isomill simply moves along or slides along those tracks that are shown in the picture here, exposing that central rotating shaft and the discs, and allowing them to be replaced with ease, so no working under loads. And so as a result of the design of the mill, the use of that ceramic media, we have this very energy efficient mill that provides ease and safety in terms of maintenance. And one thing we do often hear, though, when we are talking to people about a horizontal stirred mill, initially is that concern around the footprint that might be required compared to a vertical stirred mill, its counterpart. So on the slide here, what you see is the isomill overlaid by the space requirements for a vertical fine grinding mill. So for maintenance on vertical mills, obviously a crane is required, and space actually needs to be available to allow site to lay the shaft down when they've removed it. So the result is, in fact, that the footprint requirement when moving to a vertical mill, in fact, isn't as different to a horizontal mill as people might think. So to size and design an isomill, we've got a standardized test that's performed by accredited laboratories. So this is called the isomill signature plot. Basically, it's used to obtain the specific energy required to mill an ore or a concentrate to the required product size. It's not the same as bond work energy. It needs to be done in, typically we do it in an M4 isomill, but because there is a one-to-one scale up between the M4 and any other isomill, technically it could be done in any sized isomill. And so what you see on the screen here to the left is the laboratory scale M4 isomill that we usually do the signature plots in. And at the bottom, we've got a picture of an M20 isomill with 2 tanks and a feed pump. And one example of the application of an isomill prior to a cyanide leach is the Gidgee operation in Western Australia. At this operation, the roaster that was at the Gidgee site treated concentrate from both the nearby Fimiston processing plant, as well as the Gidgee plant itself. But due to some significant changes in the sulfur grade of the ore that they were mining over time, the capacity of their roaster was eventually exceeded. And they actually looked at a number of options for addressing this, one of which was finely grinding in an isomill. And this option turned out to offer the best value for the project. So in 2001, an M3000 isomill was installed and commissioned at Fimiston, and that was very closely followed the next year by a second to increase throughput and treat excess con. And then 13 years later, an M10000 isomill was installed at the Gidgee site itself. So that circuit comprising the fine grinding ahead of the CIL achieves a gold recovery of 92% for that particular operation. So with the addition of a fine grind, some operations may find that they're able to shift back into that area of high recovery. But what happens if we move into even more refractory material? So depending on gold associations, the dissemination of the gold, and the refractoriness of the materials, a fine grind alone may actually still be sufficient to achieve high gold recoveries. But it's not always the case. So many projects or operations will find that fine grinding alone doesn't sufficiently liberate or expose the gold. The gold may be very finely disseminated within that sulphide matrix, and fine grinding down to a size to actually sufficiently liberate it may be too energy intensive or prohibitive in terms of cost. And so where that gold isn't sufficiently liberated, trying to pass sulphide materials through a conventional leaching circuit will ultimately yield poor recoveries, as these passivating layers end up developing on leaching surfaces and ultimately halting the leaching process. So a further treatment is going to be required in order to shift from lower to higher recoveries. And so that's typically a pre-treatment stage whereby the sulfides that are present are actually oxidized. That opens up the sulfide matrix in order to make the gold amenable to cyanide leaching. And so there's several commercialized options that do exist for the oxidation of sulfides, including pressure oxidation, biological oxidation, roasting, and of course Glencore Technology's Albion process. So the Albion process is an atmospheric oxidative leaching process. It's been successfully commercialized in zinc, lead, zinc, copper, and of course in gold. The Albion process actually comprises of two very simple stages, and it is as simple as it looks and sounds. So the first stage is a fine grind in an isomill, as we talked about before, and it's the ability of the isomill to achieve that really tight size distribution, not just a fine grind, but bringing that coarser top size down. It plays an important role in terms of the downstream leaching in the Albion process. So during this fine grind, basically we increase the surface area and subsequently the reaction rates that are going to occur. And the particles themselves are brought down to a size that is so small that they're able to be leached before any passivating layers actually occur. So then we proceed into the second stage of the Albion process, and that's the actual oxidation of the sulfides themselves. So the finely ground product is fed to the oxyleach reactors that you can see in the right-hand picture here. So these are agitated tanks, and we sparge oxygen in at the bottom. Now, the design of the tanks is such that we will optimize or maximize the oxygen mass transfer rates within. So this includes the aspect ratio of the tank, which maximizes the hydrostatic head, the design of and the power to the agitators themselves, and the actual oxygen injection system. So this is done via the hypersparge, another Glencore Technology product. Basically, the hypersparge sparges oxygen at supersonic velocities, creating a very high shear and therefore very fine bubbles. So that, coupled with the other design considerations that I mentioned, allow for very high oxygen mass transfer and very high oxygen utilization, so up to 90% in these units. So when applying the Albion process to gold concentrates, the process itself is actually particularly simple. So the leach is typically maintained at a pH of about 5.5, and this is achieved by simply dosing a limestone slurry into the tanks as the sulphide oxidation is occurring. So that sulphide oxidation is facilitated by the sparging of oxygen itself. Pyrite or arsenopyrite, which are typically the predominant gold hosts, begin to oxidize and generate acid, and that acid is neutralized via the addition of that limestone to maintain a pH of 5.5, which is ideal for pyrite or arsenopyrite oxidation. On completion of the leach, there's a simple solid liquid separation, and in this process, the gold actually remains in the solids. So it's the thickener underflow than the solids that then progress on to a traditional cyanide leach. So some of the benefits of the Albion process when compared with other hydrometallurgical options, firstly, a lower capex due to the fact that it operates at atmospheric pressures. So high temperature and high pressure systems or expensive ancillary equipment aren't required to support this process. And it also results in inherently safer design. Now, the ability to operate at these conditions also means that we can target the extent of the oxidation that we want. So unlike some other processes in which 100% of the sulfides will be oxidized, whether you need it or not, we will actually target the level of oxidation that we need, the lowest amount of oxidation that we need to still achieve high gold recoveries. So in many cases, a lot of the gold projects that we work on typically find that sulfide oxidation of about 60 to 70% is actually sufficient to achieve gold recoveries of around 95%. And so as a result, we're able to target lower oxygen requirements, lower limestone dosing requirements, and as a result, lower capex associated with an oxygen plant and lower OPEX associated with reagent demand. The system's also very fast to commission, so our sites typically achieve design production within 12 months of commissioning. And as you've seen, it is a very simple process that is easy to control. If a concentrate can achieve a sulfur grade of minimum about 10%, the process will also be autothermal, so it will generate its own heat. And overall, it's a very highly robust process. So we can design this to treat varying grades in terms of sulfur or other elements within that feed, and a modular design contributes to that rapid commissioning. So to size and design an Albion process plant, there are a number of stages of test work to go through, but typically we would start off with a concept or amenability level test work. And this would typically involve a single test in which we would look at both the kinetics and the extent of sulfur oxidation required. And we design this to be a fast fail. So we throw everything we've got at it. We will typically grind it finer than it needs to be, leach it longer than it needs to be leached for, so that we can give a clear answer, yes or no, will this process work? From there, pre-feasibility and feasibility stages are based around optimization and involve a number of different tests, and these will be tailored and unique to each process or each operation. So we work very closely with accredited labs, and there are several around the world, and tailor each test work program accordingly. One important thing to note is that the Albion process can be designed and guaranteed off bench scale work only. Piloting isn't required. We can, of course, pilot if a client requires it, but it's not necessary on our end. And so that brings us to the end of the presentation today, looking at how we can work with varying depths of a deposit and add simple stages into a circuit to continue to achieve gold recovery and maximize value. So at any stage, if you have any questions, please don't hesitate to reach out to us, and we look forward to seeing you this year at World Gold.
Thank you, Beck. That was really enlightening. And thank you all for joining the webinar. That's the end of the presentation today, but our team will stay online and we're ready to answer your questions on the chat. The slides and the recording of the presentation will be available in the lobby of this webinar, which you can access by clicking on the same link you used to access the session. Thank you for attending and see you at the next Glencore Technology webinar.